Last lesson, chapter 8. Okay, objectives, we're going to determine whether a linear, exponential, or quadratic function best models a data set. Okay, this is 8.5, linear, exponential, and quadratic models. So how can we determine whether the data in the table can be modeled by a linear function? Well, we're pretty good at this. Okay, to tell if something's linear or not, we just do the linear loops. Okay, we're looking to see if we add the same thing over and over again. Okay, so how do I get from -1 to +1? I add 2. 1 to 3, I add 2. 3 to 5, I add 2. 5 to 7, we add 2. Okay, this is what we call the first differences. Okay, the differences between consecutive y values are the first differences. Okay, just like our linear loops is a way you can think of the first differences. Because the first differences are all the same, this means this is best modeled by a linear function. Okay, so what about this one? Let's see if it can be quadratic. Well, to figure out the quadratic, we look for the second differences. Okay, so just like the last one, we're going to find our first differences. So how do I get from 3 to 9? Add 6. 9 to 19, I add 10. 19 to 33, I add 14. 33 to 15, I add, 18. Okay, well, the second difference is said, okay, let's take these loops and see what the difference is in between. So how do I get from 6 to 10? I add 4. 10 to 14, I add 4. 14 to 18, I add 4. Because our second differences are all the same, this can be modeled by a quadratic function. Okay. Okay, so exponential. Okay, think back to chapter 6. So this is so check the first differences, check the second differences. Neither of those work. We're going to analyze the ratios of consecutive y values. Okay, so we're going to be doing some division. So let's take a look at this, this example. Okay, so we have 1 to 2, we add 1. 2 to 4, we add 2. 4 to 8, we add 4. 4 to 8 to 16, we add 8. Okay, definitely not the same. Okay, so let's check the second differences. 1 to 2, we add 1. 2 to 4, we add 2. 4 to 8, we add 4. Oh, still not the same. Okay, so now we're going to check the common ratio. So we're just going to take the second term divided by the first term. 2 divided by 1, 2. Okay, 4 divided by 2, also 2. 8 divided by 4, also 2. And 16 divided by 8 is 2. Okay, therefore, this is best modeled by an exponential function. Okay, so your turn to try some. Pause the video and try letter A, please. Okay, so -2 to -5, we subtract 3. -5 to -14, we subtract 9. -14 to -19, we subtract 15. -29 to -50, we subtract 21. Definitely not the same, so let's check our second differences. Okay, we subtract 6, subtract 6, subtract 6. Okay, since our second differences are the same, quadratic is the best. Okay, check this one. First differences, okay, plus 8, plus 24, plus 72, plus 216. Definitely not the same. Okay, so plus 16, plus 48, plus, I can't do that one in my head. Give me a second. 216 minus 72, 144. Ugh, not the same. Okay, so let's check our ratios. So if I do 12 divided by 4, 36 divided by 12, 108 divided by 36, and 324 divided by 108. 12 divided by 4 is 3. 36 divided by 12 is 3. 108 divided by 36 is 3. 324 divided by 3 is divided by 108 is 3. Therefore, this one is best modeled by an exponential function. Okay, this one, we're going to just figure out what's the best. The book involves having you do quadratic regression, and I'm not going to have you guys do that. That's not an Algebra 1 standard. So we're just going to determine what's best here. Okay, so let's check out our first differences. Okay, 0.21, 0.31, 0.32, and let's see. Oh, I did that one wrong. Goodness gracious. About 0.42 and 0.52. Okay, first differences definitely aren't right. So if I do my second differences, I get 0.1, I get 0.11, and I get 0.1. Those are all fairly close, so we're just going to go with quadratic. If you're curious to see how the quadratic regression works, please look in the textbook, but I'm not going to go through it. Okay, here's another one for you. Please tell me exponential, quadratic, or linear. Pause the video and try. Okay, so I do some subtraction. I get 10.5. I get minus 78. 10.6. Okay, 10.5. 10.6. Those are all fairly close, so linear works the best. Okay, so if I compare three of them, okay, I've got three different functions here. So the graph shows population models for 3 cities based on data over a 5-year period. The populations continue to increase in the same ways. When will the population of city C exceed the populations of the other 2 cities? Well, as you can see, A is linear, B is quadratic, and C is exponential. Okay, we know from studying this, exponential grows the fastest over time. Okay, so eventually city C will be the same. So what they want you to do is to start plugging and chugging. Okay, let's start with year 4, plug it into each of these functions, and I'm going to rewrite them down here. F is 3.2x. G is 0.25x squared. And then that's 2 to the x minus 5. Okay, so I just start plugging them in. Okay, so if I do 3.2 times 4, I get 12.8. 0.25 times 4 squared gives me 4. And 2 to the 4 minus 5 is 0.5. Okay, keep going all the way through. And eventually you see that right here, these two values are the same. So after year 10, that's when h of x becomes the biggest. Okay, so you just make a table of values and you plug and chug until you find something that gets you there. Okay, so just to summarize, function is linear if all the first differences are the same. Function is quadratic if the second differences are the same. And a function is exponential if the ratios are the same. So homework tonight, you're on page 349. You're going to do problems 9, 10, 11, 13, and 17. Having a great day, guys.